So hi, I'm Sam. A lot of you I've met before. Some of you I haven't. I'm looking forward to chatting later. This week I'm celebrating the paperback release of my first book. It's a book about asynchronous programming in Kotlin. Thank you very much. It's been out in digital form for a while, but now you can officially order it in print from a bookshop, so that's really cool. So why write a book about asynchronous programming? I think a lot of people, most programmers would agree that asynchronous programming is kind of annoying. It's got new concepts and new functions that you have to learn. Well, Kotlin takes that to a whole new level. You have to learn coroutines, suspending functions, coroutine dispatchers, coroutine scopes, all kinds of new stuff. And each of those new things comes with a bunch of advice and rules about when you should use it, when you should not use it, what's going to happen if you use it wrong. It can be quite overwhelming for new Kotlin programmers. And so the approach that I wanted to take in the book was to kind of say, well, instead of just giving you another laundry list of tools and rules that you need to learn, let's try and dig a little bit deeper and say, well, why do all these tools exist? What are the problems that they're trying to solve? And hopefully that lets people have a bit more of an intuition and start to program more intuitively with these asynchronous tools. And it turns out that that works really well, because what you start to find when you dig into asynchronous programming is that a lot of it comes back to this one underlying problem that all programming languages and all asynchronous programming tools seem to run into at some point. And so this problem crops up in a load of different guises and different ways, and that's one of the reasons I call it the many-headed async monster. So I'm going to try and explain that problem today. And we're not going to do any Kotlin code. We're going to do JavaScript because this is really simple. This is just a function that prints out hello world in JavaScript. I hope I've done it right. I'm not a JavaScript programmer. So I want you to imagine that you're a machine executing this function, and I want you to think of the function as a path that you're going to follow through the code. So you're going to go in at the beginning of the function, you're going to execute the code in the middle of the function, and you're going to pop out at the end. And if you imagine sort of like a map and you're tracing your finger along the code, then you're going to go into the function, and when you get to the end, you're going to return back to the caller. And this idea that a function has a single kind of well-defined entrance and exit is a really important programming principle of modern programming languages called structured programming. And it kind of holds true with any kind of different code that you could put inside of a function. So if you've got an if-else block, yeah, you're going to possibly branch down one of two different paths, but they're going to join back up, and you're going to come out at the same exit at the end of the function. And yes, a function can have multiple return points, but I want to think of a return statement as kind of like a skip forward through the function. So you might be jumping to the end, but you're still going to pop out at the end of the function in that kind of same route on the map that you would always be following. So you just pop out in the same place. And that principle, oh dear, something's gone wrong with the graphics on the slides there. You can ignore that. This principle is really important for composing code together. So if every piece of code has this same shape with an entrance and an exit, then you can do things like putting it in loops. You can think of a loop as saying, when you get to the end of this code, go back to the start. Well, that means you have to know what is the end and what is the beginning so that you can jump from one point to the other. If you have a try finally block, you can think of a finally block as a checkpoint that goes at the end of the code that says, when you reach the end, do this. So yeah, you need to know where the end is. Try catch blocks also wraps up a block of code, so you need that block of code to have this same well-defined structure. Okay, more broken graphics. This is a picture of an hourglass, if you can imagine that. So now we're going to do something a bit more interesting with our original function, and we're going to add a delay. And I want you to imagine, okay, if JavaScript had a sleep function, then that's what that might look like. And this is a nice way to visualize what we're trying to do. It doesn't work. If JavaScript did have this function, then this would have a problem because it would block your thread. JavaScript code is typically going to be running single-threaded. And if you block this thread, then your browser's not going to be able to do anything else, and your page is going to be frozen. And this is the kind of issue you run into with mobile apps, all kinds of UIs. You don't want to freeze your main thread. You don't want to stop it from doing the other important things that it's meant to be doing. So instead, JavaScript uses callbacks, so you'd write set timeout. And the important thing about the set timeout function is it returns immediately, right? And that means that the demo function that we've written can return immediately, and that means that our UI thread can get back to doing whatever important stuff it was meant to be doing before. Meanwhile, the set timeout function has queued up this second function to run in the background. So this is a callback function. That's going to run after a second, print out our message. So we still get the behavior that we wanted, but now we haven't blocked our thread by making it just sit there doing nothing for a second. So splitting up a function into two pieces like this is kind of the fundamental trick that makes asynchronous programming work. And I imagine a lot of you are very familiar with this if you've done asynchronous programming, if you've been unlucky enough to have to go through that pain. So let's do that same exercise we did before and kind of trace a path through the code and figure out where we pop out at the end. One way to look at it is you go in at the beginning, you start your timer running. After a second, you print out your message, and then you're done. And that's kind of the original task that we wanted to complete, so that's kind of the same path that we originally had. But now that's only half the story, because we have this second exit. Which after all was the whole point. That's why we wanted asynchronous programming. We wanted to be able to return immediately so that the UI thread can get back to doing its important work. So that's really important, but it's also kind of annoying because now we have this really unusual control flow shape where we have, and if you imagine tracing your finger now through this code on the map of your program, then you trace through into the function, and then you jump out, but now you need another finger because you need to point at the callback as well. As long as that callback's running, you have potentially a second path through the code that you need to be following. So this is fundamentally different from what you would see in any other function. This is a kind of new control flow structure with this two diverging branches. And this turns out to be the underlying problem that makes asynchronous programming annoying. And that is another reason that I call it the many-headed async monster, because every time you use an asynchronous callback, you end up with this diverging control flow path, kind of multiplying the branches through your program and adding these kind of new heads to the monster, like the mythical Hydra. And so if you think about the problems that you run into when you're doing asynchronous programming, you might well have run into the problem that if you're using callbacks, then you can't use loops and try-catch blocks. If I had more time, I would go into that in a lot more detail, but hopefully it's kind of intuitive that this has a lot to do with the kind of diverging control flow problem that I mentioned. If you put that demo function inside a try-catch block, for example, then that second callback function is not inside that try-catch block because we know the demo function returned immediately. That was the point. The try-catch block is done. You can't catch errors from that callback because it's not in there. You also, with asynchronous callbacks, you run into potential problems with resource leaks. You have these tasks that are now running in the background. You have to keep track of those tasks, cancel them if they run too long, make sure that they're not holding onto resources that the rest of your program wants to be using. And so a lot of asynchronous programming tools are dealing with these background tasks, which remember we never really kind of originally wanted. All we wanted to do was wait for a second, and now we have this background task that we never really asked for. Asynchronous code is also very good at hiding. So all of these potential pitfalls that it introduces into your code, these kind of background tasks and potential resource leaks and errors that are escaping from your try-catch blocks, you might not know that they're in there. Does this demo function contain asynchronous code that might be running in background tasks? You don't know until you click on it and look inside it and find out. And that's potentially a big problem because it can take you by surprise if you're not looking for it all the time. So how do we fix it? How do we make it go away? I want to do something slightly unconventional. Let's focus in on this bracket at the end of the code here. because this is kind of the crux of our issue. If we put some code before this bracket in our demo function, then that's in branch 1. That's part of our delayed code that runs on our timer. If we put some code after this bracket, that's now part of our second code path. That's the code path that's going to run when that demo function returns immediately to its caller. That second branch, don't really care about that. Never wanted to put any code in there. The thing we care about is the thing that happens after the timer. So let's just move it out of the way. Just put it to one side, add some indentation, and put this stuff back over to the left-hand margin. This is kind of how I want this function to look like. Okay, bear with me. And actually, you know what? Let's just cover that stuff up. You know, we never really cared about that. We didn't ask for it. We were forced into it. We're gonna get rid of it. And okay, you might have guessed that the reason I show you this is because it turns out that a lot of programming languages, JavaScript included, can do this trick with the async await keywords. So when you write async await in your code, you're essentially telling your compiler or transpiler to put something a little bit like those asynchronous callbacks and brackets back into your code. And this is what that looks like in our JavaScript example. If you're running on Node.js, then I think you have this set timeout function that you can await. Again, as I say, I'm not a JavaScript programmer, so it might be completely wrong. So this is a lot cleaner. It's a lot nicer to look at. But also, very importantly, it does not include that second code path. The kind of the branching tasks are still there, but because we've kind of hidden that second branch and shuffled it out of the way, there's no way to put code inside it. There's only now one branch that we care about, one path through the code that's important, and that's our main visible path in the source code. And so that means if you were to trace now through this code with your finger on the map of the program, then you go in the beginning, you pop out at the end, you know it's going to behave like an ordinary, well-structured function. And that's really cool because it means with a little bit of extra compiler trickery, which involves continuations and things, you can start to use it in loops, try catch blocks, try find loop blocks. So async await, it's not just about making the code look cleaner, it actually reopens a whole bunch of possibilities, control flow tools that were previously blocked off. So is that the solution? Have we vanquished the many-headed async monster? Well, very nearly. The one final issue, which I think is still there, is I said asynchronous code is very good at hiding. These issues can hide inside functions which don't necessarily have any advertisement that they're asynchronous when you call them. Well, you could argue that with async await, we've actually made that problem worse. If you think of async await as kind of partners in crime, then the async keyword is responsible for kind of putting in those invisible callbacks in the background in your code. And then it's the await keyword, which closes off that second control flow route so you can't use it and makes sure that you're always going down the important path that you care about. Well, that means if you use async without await, then you've created those invisible callbacks, but then you've done nothing to make them safer or more usable. And so they're there possibly causing all those same problems, leaving all those traps in your code. But they're even better at hiding. So can we do any better? I said that my book is about Kotlin. In Kotlin, we don't have the async await keywords. We have the suspend keyword. A function with the suspend keyword, it looks, or it behaves very much like a function with the async keyword. But the difference is that when you call it, it always acts as if you had used await. And so here's what that program might look like in Kotlin. That delay function on the second line, that's an asynchronous operation, but you wouldn't necessarily know it to look at it. And that's because as the programmer calling that function, you don't need to know that that's an asynchronous operation. You don't need to remember that it is. You don't need to look inside it. It will just do the right thing when you call it. And that means that there's nowhere for background tasks to hide. There's nowhere for errors and resources to escape into these control flow weird dead ends that you never asked for and never wanted. So that causes some problems of its own. Background tasks are kind of useful sometimes. Sometimes you want them. And so that means that in Kotlin, you have a whole bunch of extra tools for creating and managing these background tasks. That's why the book is 250 pages long, and this is a 15-minute talk. If you would like to find out more about that, then I would be thrilled if you would check out my book. You can find it on the Pragmatic Programmer's website. I also have a second book that is also available in digital form about Kotlin design quirks called Kotlin Brain Teasers. Two other pieces of recommended reading. One of them is the definitive article on this control flow problem with asynchronous programming about structured concurrency in various languages and how you solve that problem. And then the second article, what color is your function, is kind of about why asynchronous programming is so annoying and how it's kind of an unsolvable problem. So I'll leave it on that note. And thank you very much.
Thank you very much, now. That's great. So I'll start with one question. So these languages which actually have like async await and suspend built into the language are highly dependent on the runtime giving you that support framework for it. Because if that runtime controlling what's happening underneath, then it could just almost go, explain.
So, well, give me a little bit more. I don't quite understand the question.
So, like, when you say, this thing's going to go off to be asynchronous,
Yeah.
there's a subsystem as part of the language runtime which is actually controlling those tasks so that they can actually be executed either in a single thread thing through like a job queue or actually dispatched up to multiple concurrent tasks again. There's something in the runtime that supports that.
Yeah. And that can, as you say, take any number of different forms. JavaScript, event loops in Kotlin. Kotlin runs on any number of different platforms. JVM with multi-threading or virtual threads. JavaScript or in the browser in WASM with single-threaded or native with one thread or many threads. And so Kotlin's coroutines are designed to provide a kind of unifying abstraction that will allow you to treat all of those kind of interchangeably. So to write code that will be concurrent asynchronously on a single thread or will parallelize potentially on multiple threads. You just write it once and it runs the same wherever. But that means you need a lot of tools and abstractions to make that happen. Hence all of these dispatches and things. Did that answer any or all of the question? Yeah.
Well, any questions from the audience?
More of a question, more of a thing to say JavaScript before the async in a way came along and promised to do that, so you have it's definitely got a lot better.
Yeah, I was lucky enough never to have to do a lot of JavaScript, but I did do some jQuery back in the day, so I was kind of nodding along when you were talking about that. And yeah, async in jQuery, I'm familiar. Yeah, I remember the nested callbacks and yeah.
So as a kind of counter, I know things through JavaScript. So callbacks, there's promises, and then async await, and now I'm actually written a bit of Kotlin. And all of the dispatches and the scopes, I still find that I write Kotlin in the back end, so maybe you get a bit more experience around that. I find it super confusing.
Yeah.
Is it worth the price of admission?
It's worth the price of my book.
Yeah.
that you are the target audience. But no, I mean, in all honesty, I absolutely agree with you, and that is really the reason that I wanted to write the book, is because, on the one hand, Kotlin is kind of selling its approach to async as, well, we're solving a lot of problems that haven't been solved in a good way before. On the other hand, you look at it and you think, well, this is madness. There's, a whole bunch of new concepts and new tools I have to learn just to make a network call. And I compare that to what Java is doing with its virtual threads, and you think, well, this is just this, it should be easier, right? You know, Kotlin's approach should be easier. And I think, you know, that they're trying to solve a very big problem of bringing together all of these different platforms and targets and trying to make one asynchronous programming model that works for everything. And it's a huge problem to try and tackle. And I am looking forward to seeing how it evolves and whether we find ways of simplifying it. Because at the moment there's a barrier to entry. And I think a lot of the things I explain in the book hopefully help to make it make a lot more sense, but it's still a long book, and we shouldn't need a long book just to make asynchronous programming make sense. So I agree, yeah.
Any more questions? Okay, I'm going to say thank you to Sam.
Cool, thank you.